So we're looking at page 83 and talking about Taylor polynomials, Taylor approximations. So the blurb here, polynomial functions can be used to approximate other elementary functions such as sine x, e to the x, basically transcendental functions, things that aren't, and I kind of address this, I definitely address this in the third tech assignment, but the idea is to be able to map a transcendental function using a polynomial function. The idea being that it's easier to do calculus and things of that nature to polynomial functions, especially if you only need it over a certain interval, right? The accuracy level to be over a certain interval, than it is to do it for certain transcendental functions. So let's take a look at y equals the sine of x. I'm just going to pop that in real quick. I hit the wrong thing. I hit mode for some reason. Sine of x, and then I'm going to put in this brand new function x minus x cubed over, so x cubed divided by, well, 3 factorial. I'm not going to type in 3 factorial, I'll just type in what it is. It's 3 times 2 times 1, which is 6, and then plus x to the 5th. So we're looking at some sort of alternating series here, or at least a part of it, a partial sum. But anyway, that's besides the point for now. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 5 times 4 is 20, 3 times 2 is 6, 20 times 6 is 120. The 1 is irrelevant, right? And so I'm going to hit graph, and you see here that, I mean, my graph is a little outrageous. But if I bring it in, you see at least for a small interval around 0, we're looking at a polynomial function that does the same work as the sine function. All right? So when you start thinking about derivatives and antiderivatives and evaluation of expressions and things of that nature, we can come up with a reasonable approximation using this, as long as we only care about it going over this particular interval, which looks like it's pretty solid in terms of an approximation if we're only going from, let's say, negative pi over 2 to pi over 2. All right, because that's where it mins out going to the left and it maxes out going to the right. All right? So the big question, and I think it's a pretty necessary question, would be, all right, well, that's great. How'd you get that? All right, so in order to do that, we're going to come up with the Taylor polynomial. The model is given as c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared, and so on until you get c sub n times x minus a to the nth power. So what we're going to do is find some derivatives, all right? Because this is just a polynomial. From this, we're going to invent the Taylor polynomial. All right. So if we were to take the derivative of this, the constant part, c, we can assume c is a constant or a constant multiple. That's just going to go away. All right. So I'm going to take the derivative, and the first thing I'm going to do is I'm going to get rid of the c sub 0. All right. And when that happens, I can use a little bit of chain rule here. I'm going to raise this. I'm going to show this being raised to the first power. All right. So 1 times c sub 1 is c sub 1, x minus a to the 0th power, plus 2c sub 2, x minus a to the first power. The derivative of the inner function, since we're taking the derivative with respect to x, is just going to go to 1. So it becomes irrelevant. So plus 3c sub 3 x minus a to the 2nd power, and we can carry this on and on and on and on until we get to n c sub n times x minus a to the n minus 1. All right. Now it's pretty easy to see that this is going to kind of get a little out of hand on the high side after too long. Well, after we go down the line. All right, but at least in the early goings, it's kind of simplifying a little bit in a nicer sense. All right, so I'm just going to do a quick duplication here. There isn't much simplifying to be done here. It's just a matter of just kind of wiping out an exponent, wiping out an expression. So this part, this is a 1, so that disappears. And that 1 doesn't really need to be there. All right. I mean, in our minds, it's great to have it there, but it doesn't need to be there. Right. Now, bear in mind that if this is an infinite situation, after the n-1th term, we would still have another term and another term and another term. Right? It could go on and on and on, but we're only really kind of focused on the low end of this for now. All right, so let's just kind of go and see how this plays out. All right, so the second derivative, well, the c sub 1 is going to go to 0 now. All right, and so again, we have the assumption of a power of 1, so we're looking at 2c sub 2 times x minus a to the 0th power, makes that irrelevant because that's going to go to a 1, plus 6c sub 3 x minus a to the 1st power, and on and on and on and on and on until you get to, so plus dot dot dot, you're going to have the n times n minus 1 c sub n x minus a to the n minus 2 power. All right, so let's do it again. The third derivative, constant goes to 0, so we'll have 6c sub 3 x minus a to the 0th power. All right, then you'd have more and more terms along the way, so plus a bunch of other terms along the way, plus n times n minus 1 times n minus 2 c sub n x minus a to the n minus 3 power. All right, so you see here that the level of the derivative is consistent with the number that's being subtracted from n. That comes into play in the next step, because now we can start to kind of draw inferences and conclusions. We know that every step of the way we're going to have a c sub n. So I know that that's going to be part of it. All right. The x minus a will eventually be raised to the n minus n power. All right. Now, as far as the first term, I don't want to write out n times n minus 1 times n minus 2 times n minus 3 times n minus 4. But what I can do is I can make an inference here and say that, okay, well, it appears that for the third derivative, we get as far as n minus 2. All right. So let's hang on to that thought for a second. I'm just going to shunt this over here for a sec. So we're looking at, we would have the n minus 1, the n minus 2, we'd probably have an n minus 3, an n minus 4, an n minus 5, and so on, until we would get to, well, n minus 1 less than n. So n minus 1. Well, that's the same as saying 1. Right? For a couple of reasons. One is because there's one term of difference between n and n minus 1, but also if you distribute the negative, you get n minus n, which goes to 0, and then you'd be left with a positive 1. So all of this boils down to an n factorial times c sub n, and then the n minus n power is going to make the binomial go to 0. I'm sorry, go to 1. exponent goes to 0, the whole binomial will go to 1. All right. So that's information. It's useful because it's telling us that this thing actually, instead of getting really, really complicated, actually gets really, really simple for larger values of n. All right, for more terms in the sequence. All right. So now looking at it from the perspective of a, so if I want to center this around some value a, where x is equal to a, that's going to really wipe out everything. If you just kind of look at this, you look at all these terms here, every one of them has an x minus a. A minus a goes to 0. So the first entry here would be a c sub 0. The second entry would be what you would get if you plug in an a for each term in f prime of x, which is going to make every one of these guys go to 0, which means you'd be left with just a c sub 1. Now, you can follow a little bit of logical reasoning, but you could also just kind of see that the same relationship is holding true for f double prime of a. All of these will get wiped out. You'd be left with 2c sub 2. Get a fresh new color in here. I'm going to go with green for those keeping score at home. So everything except for the first term will get wiped out. 6c sub 3. All right. So if I just chuck in some coefficients here, I'd have a 1. Go back to the red. I'd have a 1, and a 2, and a 6. I'm like, oh, that's an interesting pattern. All right, at first glance, it looked like whatever the coefficient was going to be the same as a subscript, but that's not the case. As it turns out, we're looking at some factorials, all right? Because this is the same as saying, and I'll write it here, 1. Let me put the c sub 0, c sub 1, c sub 2, and c sub 3 first. The result is a 1, but that comes from some value that resulted in a value of 1, to overuse a term. So you look at, for example, a 6. 6 is the same as 3 times 2 times 1. That's 3 factorial. 2 is the same as 2 factorial. 1 is the same as 1 factorial. And you're like, another 1 factorial? It's actually 0 factorial. And so we look at this as the 0th derivative. We haven't taken a derivative yet. The first derivative, the second derivative, the third derivative. So that would make this the nth derivative. All right, so n factorial, which we already kind of discovered over here, c sub n. But we already knew that because this expression didn't contain any x minus a's anyway. It all just kind of worked itself out. So we already had the last one, which gave us an n factorial. All right, so now what we can do, if we just kind of look at this and say, all right, well, if I need to figure out a coefficient, so if I take this and divide it by n factorial, I've now discovered a relation that will allow me to determine some coefficient of the expression, because again, the only thing, I mean, we'd have to know what the a values were. That would have to be either given to us or an assumption that we would make. A for assumption if you want. The x's are going to be built into the polynomial. We would need, in order to make this polynomial equivalent to the transcendental, we would need to know what the coefficients were. All right, so now we have a way of coming up with that. C sub n, any of the coefficients, would be 1 over n factorial times the nth derivative evaluated at x equals a. So now we have a rule. We have something to work off of.